Today we're taking a look at Chapter 2, and we will be beginning with Section 2.1. In this chapter, we're looking at basic set concepts, and in 2.1, we're taking a look at some symbols and terminology that we will be using throughout the chapter. First of all, when we're thinking about sets, we're talking about collections of objects, and what we find is that human beings have long liked to place similar objects in groups or collections. If you think about the term set, we talk about a set of dishes, a set of books, a set of encyclopedias, a set of tires, and so forth. Now, set names are designated with capital letters, such as capital A, capital B, capital C, and so forth. Much of what we're studying in this particular chapter was developed by the German mathematician Georg Cantor, and he lived in the mid to late 1800s. So we're looking at the ideas that he has come up with. Now, we get into some definitions, and just a point of notes. What you want to do as I'm going through and lecturing is you want to jot down any additional information you think will be helpful on the edge of the notes here, and we'll be working some examples. So you should do those along with me. Sometimes I'll have you pause it and work it, and then we'll correct it together. So you want to keep those notes, and then you want to keep these notes in a 3-ring binder of some sort, because you will be able to use those on the exams in the testing center. So I do recommend that you save these notes for that purpose. Okay, our first basic definition is elements or members of a set. These are the objects that belong to a set, and we have two symbols. Is an element of, it looks like a funny E, simply means that something belongs to the set, and of course is not an element of simply has the hatch through it, the cross hatch that says something does not belong to the set. So for example, and you'll notice that when we write sets that we use what are called, these symbols here are called braces. So those are used to enclose the elements of the set. So what we're saying is 1 is an element of the set containing 1, 2, 3, 4. 5 is not an element of the set containing 1, 2, 3, 4. And you'll notice how I read this, the braces, as the set containing. Now, we want the braces, to use the braces, I've seen some students use parentheses. Parentheses are used for different, are symbolic of different ideas rather than sets. So please make sure you use braces. I also want to point out, if you have braces in a case like this, notice that the braces are around the 4. So if we were to decide whether to put E is an element of or is not an element of, because the number 4 does not have braces around it, it actually is not an element of the set containing 1, 2, 3, 4. So that's kind of a fine distinction there. 4 is an element, but the set containing, notice the set containing 4 is not an element. We would have to have the set like this, to be able to say that that set contains the set containing 4. So we'd have to have braces around the 4. Now, there are 3 ways to designate a set. First of all, we can use what is called a word description, where we just describe it in words, the first 5 counting numbers. The second way is the way I listed the setup here. It's called a listing or a roster. We simply use braces to indicate we have a set, and we list the elements in that set. The third type of notation is more or less a combination of the first 2. It's called set builder notation. And the way we read this, and you can see it's the set of all x, the set of all x. And let's see if I can highlight with a different color. Such that, that line there is such that, and then x is one of the first 5 counting numbers. We simply use a word description there. So it basically exactly matches what it says in the word description. Okay, so the set of all x such that x is one of the first 5 counting numbers. Okay. Now there are some important sets that crop up over and over again. We have the natural or the counting numbers. These are the first. This would be the first set of numbers you learned in kindergarten, maybe in preschool. Counting the numbers used for counting, such as counting the number of coins you have, or counting the number of pencils you have, crayons you have, that kind of thing. Okay, whole numbers, we add in the number 0. Integers, we take the opposites of the positives and add those to the set. That gives us the set of integers, and notice that the ... here indicates it goes infinitely far in both directions. Both the natural and whole numbers only go in the positive direction, infinitely far. But integers go infinitely far in both the positive and the negative directions. And rational numbers, it looks like part of that got lost in the translation. The set of p over q such that p and q are integers and q is not equal to 0. Remember that we're not allowed to divide by 0. Division by 0 is undefined. So that's the reason we have, whoops, let's spell that right. Division by 0 is undefined. So let's see, D-I-V-I. Okay, now I've got it. Division by 0 is undefined. So that's the reason we have that little notation right here. Okay, the real numbers, the set of numbers such that x is a number that can be written as a decimal. And irrational numbers, set of all x such that x is a real number and x cannot be written as a quotient of integers. It turns out that rational numbers are either repeating or terminating decimals. And irrational numbers are non-repeating non-terminating decimals. So basically what happens is the real numbers are made up of the 2 sets, the rationals and the irrationals. And what would be an example of an irrational number? You might ask about that. Let's talk about rationals first. Rational numbers we can write as a ratio of integers. So for example, 3/4 we can write as a terminating decimal. It ends. 1/3 would be a repeating decimal. It's 0.3 with the 3 repeating, and we put the bar over it to indicate it repeats. Those would be rational numbers. Irrational numbers are square roots where we do not have a perfect square radicand, the radicand being the number inside. So the square root of 2 would be irrational. Pi, what we use in geometry with circles, 3.14159 and so forth. It's a non-repeating, non-terminating decimal. And I can even create one just by adding